Okay guys, what we're going to start doing now is actually looking at the practical applications of sinusoidal functions. And one of the best things that it helps us to do is help us to describe circular motion, to relate that as the height of something circular over time. It's a very common application of it. And so one thing we're going to look at, because it's state fair times, we're going to look at a Ferris wheel example. So if you look at this problem here, it says you're standing in line to ride the Texas State Ferris wheel at the State Fair of Texas. As you're waiting, you notice that while riding, a person's distance varies from the ground sinusoidally with time. So we know this is going to be a sinusoidal function. All right, so we read the official's guide to the State Fair of Texas, and it tells me the diameter of the Texas star is 212 feet. And then we notice that it takes 82 seconds for that Ferris wheel to make one revolution. And then as I approach that loading dock, it says that passengers are loading 8 feet from the ground. And then when it's finally our time to load, they load a few other cars. So we get on the Ferris wheel, it kind of pushes us back some, and then as it loads a few more people. And then when it finally is fully loaded, then it starts to turn. So we're going to time how long that takes. So from the time we're on that Ferris wheel, it takes us 50 seconds to reach the top. Okay, so something to think about there again with that Ferris wheel. Basically, you're on that Ferris wheel at the bottom. So then it loads more people, that moves you back this way before your Ferris wheel actually starts to turn. So that's kind of what's going on there. Okay, so first thing, we're going to figure out some information about this Ferris wheel. We want to know how high that Ferris wheel is from the top. Alright, so I know that the Ferris wheel has a diameter of 212 feet, and it starts loading 8 feet from the ground. So I take that diameter, add it to where it starts. That tells me where the highest point is going to be. Alright, so next part I want to figure out is what time that stopwatch will read when I get down to the bottom. So I know it takes 50 seconds to get to the top. Okay, and again, that was a little bit different because I started farther back before I actually continued to go. But if it takes 82 seconds for one revolution, then for half of a revolution, it's going to take 41 seconds. So that means it is going to take me 91 seconds. It will be at 91 seconds when I am finally back down at the bottom. So next question asks is how much total time will it take to reach the top for the second time? So again, at this point, I'll have 91, and I'm going to add another half of a revolution, and I will be at 132 seconds. Or I could have done 50 plus 82, and that puts me at 132 seconds still. Okay, so what we're going to do now is I'm actually going to draw a graph of what's going on here. And I'm going to draw it over here on the side where I've got a little bit more space. Okay, now whenever you're drawing these, make sure you guys label your axes so you know what all this stuff stands for. Alright, so my independent variable, my x, is going to be my time. Okay, so I'm going to mark some of the times that I know on here. I know some heights that are going to be on my y-axis. Okay, so my y-axis is going to be my height. So my y-axis, let's do that one first. That's going to be my height, and that is in feet. So the highest point that I'm going to need to mark on here is the top of the Texas star, which is at 220 feet. Then the lowest point I'm going to mark on here is when I start loading on this Ferris wheel, and that's a height of 8 feet. Alright, on my x-axis is going to be time, and that is in seconds. So what I'm going to do here is I'm going to mark those points that I figured out in my question. So the first point I knew is from the question. It tells me it takes 50 seconds until I reach the top of my graph, or to the top of my Ferris wheel. Then from answering those questions, we realized at 91 seconds I would be at the bottom, and then at 132 seconds I would be back to the top. So we said it varied sinusoidally, so I'm going to connect this as part of a sine wave. So there is my graph of the situation. So what we're going to do now is after we have the picture, we're actually going to write the equation of this sinusoid and use that equation to answer some questions. And I'm going to go ahead and write that here because it'll be a little bit simpler while I'm looking at my picture. So if you guys remember, we've done this we've seen this equation a few times now. And if you guys have forgotten how to write these equations, you might want to go back and look at some of your old notes or quizzes or come in for tutor and ask some questions, because you are going to have to be able to write these equations in order to answer these questions. So we're going to find all these different parts. Alright, so we're going to go ahead and find these actual parts. So we're going to start with C. And if you guys remember, C is my vertical shift, or the height of the middle. Now the middle actually is not listed on here, so we actually need to figure out on our own what that's going to be. But if you think about halfway in between 220 and 8, it's kind of the average of those two numbers, the midpoint of those two numbers. So I just add them together and divide by 2. So 228 over 2 is going to give me 114. So that middle here is at 114, so that is my C. Okay, now I'm going to find my A. And my A, if you guys remember, A is going to be the amplitude. So it's the height from the middle to the top. Or if you wanted to, it could also be the height from the middle to the bottom. Both those numbers should be the same. So it's either going to be 114 minus 8, or it's going to be 220 minus 114. But either way, that number is going to be 106, and that is my amplitude. And now remember, you can write these graphs as sine or cosine. I'm going to go ahead and write this one as a cosine graph just because I know where my highest point is. It's going to be a little bit simpler to write it that way. Okay, now B, if you guys remember, B had to do with our period. So B was equivalent to 2 pi divided by my period. And so if I look, I can write this. I need to find my period. It's the distance, basically how long it takes to make one revolution, which we actually know from the question is 82 seconds. Okay, but if I didn't know from my question, I could also look at my graph. And it goes from a high point to a high point. It completes one full cycle still in 82 seconds. So my B number is going to be 2 pi over 82, or I'm going to go ahead and write that as pi over 41. So then the last part of my equation is going to be x minus d, and d, if you guys remember, d is the horizontal shift, and the phase shift. And the phase shift for a cosine function is a high point. So I'm going to find a high point on my graph, and that x value of a high point is 50. So this is going to be x minus 50. And that is my equation of the graph. Okay, so what I'm going to do is I'm going to rewrite this on the second half so we can use this equation to answer some questions about this situation. Alright, so using this equation, we're going to try to predict my height at certain time intervals. So what I'm really evaluating here, if I want to know the height, if you guys remember from my graph, my height was my y. And my time was on the x-axis. So really what I'm evaluating here is this function at 15. So f of 15, I just take 15 and plug that in for x. So all I'm doing is 114 plus 106 cosine pi over 41 x minus 50. And that x is getting replaced with 15. And this is going to help me see my height at 15 seconds. So if I just typed it in my calculator, if I watch my parentheses, and I make sure my mode is correct, and my calculator's going a little slow here, when my x is 15, that's going to give me a height of about 19 feet. Or 19.006 feet if I'm doing 3 decimal places. Okay, if I want to evaluate this function, if I want to do f of 75, again, same thing. I'm going to take that 75 and replace it with my x. The last one's a little tricky because it's 5 minutes. Now remember, my x-axis was in terms of seconds, so I actually have to evaluate this not at 5, but at 60 times 5. Which is 300. And I'm going to show you guys one other way to get this besides just typing this whole thing in. And we're going to look at our calculator for this. So what I'm going to do is I'm going to go ahead and go to y equals, and I'm going to type in that whole equation. 114 plus 106 cosine pi over 41 times x minus 50. Remember, I did not close my parentheses right there after that pi over 41 because I'm taking the cosine of the entire thing. So I'm going to check my mode, make sure I'm in radians, and I am. And what I want to do first is I want to get a good window. So I want a window that matches that original graph. So my x-min is the smallest time. I'm never going to have a negative time, so my x-min is going to be 0. My x-max is how many seconds I want to look at. So if it takes 82 seconds for one revolution, let's say, let's look at 3 revolutions. So let's do 82 times 3. My scale is just how often I have those little tick marks, so 11 is good enough. Well, let's go ahead and make it 10 so it's a little clearer. All right, my y-min is the lowest height that I need to look at. And if you think about that, that minimum height we said was 8, because that's when I start loading cars. Then the highest point is my y-max. The highest height I reached was 220. And then how often I have those little tip marks, so we'll just make them every 10. So now I should be able to see a good picture. Here's my height on my Ferris wheel. So as time goes by, these are my height. This is my height as I carry on in this graph. So again, like I said, there's a little bit of a shortcut to find some of these heights. If I do t equals 15, that's an x value. So if I do second calc, where it says value there, it tells me x equals. And I can type in what x equals. At x equals 15, I get 19.006 seconds. Or sorry, 0.006 feet. So at 15 seconds, that's my height. All right, let's do at the value of 75. I'm at 78. Okay, let's do a value of 3 minutes, which is 5 times 60. All right, and it tells me I have an error. And the reason I have an error here, we're actually going to go ahead and look at it. Okay, so the problem is what I typed in there. So if I change that to 300, I'm still going to get that same error. And the reason for that is in order to do this, my window has to have at least an x value as big as what I'm typing in. So my x max here has to be at least 300. Whoops, and I changed the wrong thing there. That x max has to be at least 300. So now I can go ahead and regraph this and find that value, and it's actually going to show me what that is. And it's going to go a little slow, but we'll actually be able to evaluate it. Okay, so it tells me at 300 I've got a y value of 2.15. It's really small, 060. Alright, so that gives me all of my y values. Alright, so let's look at the next question that we have here. Oops. So my next question here, I want to see how high I was when I started my stopwatch. Okay, so when I started my stopwatch, that means that's a time of x equals 0. And then wants to know, was I moving up or was I moving down at that time? Okay, so we're going to look back at my graph picture here. So let's go back to my calculator. And let's see what's happening at x equals 0. Okay, so let me try and make this a little bit bigger. Okay, so let's see. When x equals 0, what does it tell me? So it tells me that my y value is 32 feet. So I'm 32 feet in the air before I even started to move. And then after that, if you look, that height decreases. So that means after 32 feet, I am going down. Okay, so what that means here is when I started my stopwatch, that told me my height. And then I was moving down as I started typing, or started timing. All right, now the next part's a little bit different. It wants to know what is t, okay, when I'm 100 feet off the ground for the second time. So this is telling me that y is equal to 100. And instead of solving this the way we did yesterday when we were evaluating it, we're actually going to look at a little calculator shortcut here. Okay, so this is a good way also to check your answers when you're solving algebraically. So I want to know when y equals 100 what I'm going to be at. So what I'm going to do is I'm going to go to y equals, and I'm actually going to type in y equals 100. And if you look at your graph, you can see it intersects 1, 2, 3, 4, multiple places, because I'm going to be at, if I keep going up and down, I'm going to keep going past that 100-foot line. So there's the first time, there's the second time, there's the third time. So if I want to know this x value right here, what I really want to see is where do these two lines intersect. So I know how to do that. Second, trace, intersect. Okay, and I need to make sure this little cursor here is close to that second dot. So I'm going to move that with my left and right arrows. I can move it closer to that second place. And once it's close to the second one, if you guys remember from solving systems, it's enter, enter, enter. And then it tells me when x is 72.229 seconds, my y is at 100 feet, and that is the second time from looking at my picture. Alright, so the last question, it wants to know the fifth time that I am 175 feet off the ground. Okay, so I'm going to do that the same way. I'm going to change my y. My y is going to be at 175. So I'm going to look at my graph, and it's going to graph the whole thing again. And I'm going to find the fifth place. There's 1, 2, 3, 4, 5. Okay, so what I'm going to do is I'm going to try to find that fifth place. So I'm going to do second, trace, intersect, and I'm going to move that dot by pushing my left and right arrows. I'm going to move it close to that fifth intersection. It doesn't have to be right on it, it just needs to be the closest intersection to your cursor. Enter, enter, enter. And it tells me I'm at 175 feet at 201.502 seconds. Alright, so those are just a few different applications of sinusoids.